In this video, I'm going to share a simplified version of our internal process on how we review electronics projects for EMC and EMI control so that you can start implementing this strategy whether for your clients or in your own company and projects and start saving thousands of dollars and pass EMC tests faster. To show you this process, we're going to perform a review for a printed circuit board that's been making waves online with its open source project files. The board we're talking about is, of course, the minimum carrier board, one of the smallest carrier board available for the Raspberry Pi Compute Model 5, and it features high-speed interfaces like an M-key slot for PCIe or AI accelerators, gigabit Ethernet, HDMI output, and much more. So there is a lot to unpack in this design. And along the way, I will share useful tips and tricks and show how to fix specific issues so that you can apply them to your own designs and system. Most of these fixes are independent from the project final application, so you can apply this to any projects. All right, the project files are available on the GitHub repository called the CM5 MINIMA Revision 3, and here you can get an introduction of the project, and it also shows how the board looks in reality. And I have to say, it's a really beautiful design. So the board was designed with KiCad, which is a powerful free software tool that's now being used more and more for professional PCB design. And I actually created a complete course on how to design professional circuit boards with KiCad. So if you're interested, you can check it out on my website. Now let's take a look at the key features of this project. So this project is packed with really interesting details, and the design itself looks clean and well thought out at a first glance. So in the repository, we have the PDF schematics. I have for getting started guide, and also the documentation on how to flash the operating system, which is always a nice touch with an open source project. There is also the information about the casing, which is actually quite important when it comes to parasitic coupling, interference, and also electrostatic discharge protections. And also the keys affect how much the board might radiate into the environment. So it's a good source of clues about potential emission paths and how they might couple to the nearby devices. And finally, we have the details about the PCB stackup, where we can see that this design uses 6 layers. 2 of them are return and reference planes, while the remaining 3 layers handle signals and power distribution. So it already looks like a solid structure for high-speed design like this. And it would be interesting to see how those layers have been arranged and routed once we open the layout. So because the layer order is extremely important, but we have to verify that the layers are paired together so that they are placed with the correct distances between each other's in order to reference each other's. So now let's start analyzing the schematics so that we can get a good understanding of the system. So first impression, everything looks quite clean and well organized. And personally, I would have added a bit more information on the first page to make the navigation easier. So things like a proper project title, front and back 3D readiness of the boards, and also a simple block diagram or the description of the main functional areas. Because it helps anyone reviewing the design quickly understand the structure and the purpose of the system without having to scroll through multiple pages. For example, the USB-C connector appears to be the main power input of the board, and here adding a small title or even a note with an expected input voltage range or even the current rating will immediately give the context and also help trace the power flow through the system, which is especially useful when performing an EMC or power integrity review. Positive note here is that we already have the ESD protection component in place, and these are meant to protect against the ESD, so electrostatic discharge, also the CDE, which are the cable discharge events, and EFT, which are the electrical fast transient, all of which are common sources of problems in these electronic systems. So from the schematics, we can see that the Compute Model 5 is powered directly from the VBus line, which includes also some bulk capacitance for energy stability. So one quick tip in here is to avoid placing the capacitor with the multiple sizes, sort of to catch and filter more frequencies. So the classical large 1 microfarad capacitor and then small 1 nanofarad capacitors. Because as I talked already in depth in my course for EMC EMA design, this creates a phenomenon called the anti-resonance effect, which will increase the impedance at specific frequency points. So creating peaks of impedance and a reverse effect of what we want in the first place, which is actually to reduce the impedance of the power delivery network. And avoiding these peaks of impedance is extremely important when we have these digital circuits like this one here, where we don't have a constant energy demand from the ICs, but we have these transients of energy which have a vast range of frequency involved. So this essentially means that the power delivery network, or the PDN, needs to be designed with a low impedance, not only out one frequency, but for a large spectrum. So moving forward, we have the main functional blocks, the CM5 module itself, the Ethernet, the interface, and the USB connection. I also noticed there is some change-log notes here. And personally, I prefer to keep those on the last page of the schematics, or together with the mechanical information where I keep the mounting bolts. Because that way, the main schematics page stays cleaner and also it's easiest to read. And this becomes more and more important as the complexity of the project increases, but also as the number of the revision increases together with the log changes. So here on the right side, we find the HDMI output section, the PCIe M2 slot, and the DSI CSI interfaces. And finally, we have the input and output block, which handles the various input and output signals. So notice that we have many high-speed interfaces that could be problematic if not handled correctly. So each of these sections will be interesting to analyze for potential coupling paths or layout sensitivities once we move to the PCB review later on. Now let's focus a bit more on the USB power block. So this is where the energy comes in. And so it is one of the most important points of the circuit because the current flowing in and out of the board will have to go through this point. And so here I can already see some improvement and some things to watch out for. So the first comment is about the connection of the shield connector. Because if the shield of the connector is directly tied to the board's ground net, which is in this case also acts as the return and reference plane for the signals, we have to be careful. Because if we later decide to add filters at the connector input, so before the signals enter or exit the port, for example, using a common mode choke, then this direct connection to the return and reference plane could completely bypass those filters and make them actually ineffective. So it's really important to pay attention to how the shield is connected to the rest of the system. And ideally, the metal case of the connectors should have a low impedance connection, preferably a full 360-degree contact to the chassis of the device, which in this project it seems to be a nice metal enclosure as shown on the GitHub page. So this kind of connection helps extend the Faraday cage effect provided by the connector shell and the chassis and continuously through the shield of the cable. So we want to avoid then the so-called pigtail connection where the shield of the cable is connected through a thin and high impedance wire connected to a single point of the connector case instead of having a 360-degree connection. Because this creates this high impedance path for high frequency currents, breaking the shielding continuity and then allowing unwanted common mode currents, which translate into emissions or susceptibility issues. And this is actually one of those EMC details that's easy to overlook, but can make the difference between passing or failing the EMC compliant test. So always double check how your connector shields are terminated and how they integrate with the chassis and filtering network, as well as the printed circuit board. Then the next thing to watch out for here are the CC1 and CC2 lines. It looks like they are coming directly from the outside the board straight into the computer module. And so that's something to be careful with, because if these lines are properly protected, they could act as an open door for interference to reach the CM5 module and potentially disrupt its operation. And the same ideas apply to all external connections. So not just this connection here, but any signal or power line that enters or leaves the board is a possible entry point for noise. So we need to make sure that each of these paths has the right protection network in place, whether that's a transit protection or a filtering component and so forth. So the goal is to ensure that if the interference appears at the board input, we can then efficiently reject it and safely guide it, or to dissipate its energy before it even reaches the sensitive circuit inside. So this is from the point of view of immunity and EMI. Regarding the point of view of emission from our board to the external environment, we can also place the filters before they go out over our board. So before they spread out into the environment. And this is also why we place these filters close to the connector, so that we can also use the chassis of the devices to improve the containment of these emissions. So like I said before, creating these Faraday cage effects, which in most cases, the Faraday cage is not going to be a complete Faraday cage, but it will still help us to handle these emissions and to contain within the spray. And so to do this job, so to filter these emissions, In most cases, we can use the pipe filters, which are so effective for mitigating both emissions and immunity to the EMI, because they can act as a bidirectional filter, if you will. So this is also one of the topics discussed in the filtering section of the EMI design course. So I don't want to go too much into details in here because you can check this resource there. The other comment in here is regarding the description of the net. So the data lines of the USB are differential per line. So we need to make sure that this is specified on the schematics so that the layout engineer, which can be us or someone else, knows that it has to take extra care of this net. So here we can either place a differential per signal symbol to denote it, or we can also change the color and thickness of the wire we use, and to add a small note as a legend to explain the choice. And we can write on a simple note that these, for example, are differential lines and need to respect certain impedance requirements and so forth. So we will also need to create a specific net class for this net, where we define the characteristics of the transmission line, which makes it not only visible on the schematic, but carries also this information in the PCB design tool later on. So when we have to design the layout, then either us or the layout engineer can use this information to create the layout according to the specifications. Okay, now let's move to the Ethernet block. So the first comment on this page here is regarding the direction of the design. Typically, we want to have inputs on the left of the schematics and output on the right. So this will allow us to quickly identify the energy flow direction. Especially when we have connectors like this one here, it will be best to place this on the left and then have the output of it, so the input of the CM5 on the right. And this is essentially an adopted convention that is used in the electrical world to standardize and simplify how we read the schematics. Perhaps though, the design here meant this as an output connection. So regardless of this, I think is a good tip to share for those who don't know this yet. Then we can see that we have the ESD and transient protections. And here, having a quick note on the schematics that guides the PCB layout is also really important, especially when the layouter and the schematics are not done by the same person. So the schematics should be set in the direction and instruction for the layouter to understand how to best design the board. Think about when in the future you're going to pick up the design. You're also most likely not going to remember the details of this project. So you want to create the best documentation possible while the knowledge is still fresh. And this is also important because you're most likely going to share this documentation not only with your company, but also to others. For instance, in case of certifications, you will have to provide the schematics so that they can be analyzed in terms of safety and so forth. So you want to have a clear and well-documented documentation. So this is also why having more information regarding the data speed that this particular interface is going to handle will be more useful here. And also, as I already mentioned for the USB data lines, would be useful to have here the net directives and the net label to distinguish the differential pairs. Okay, moving on, we see that we have the MP1 and 2 connected to a 0-ohm link resistor to the GND net. So this is often done to have freedom to choose whether to directly connect the connector case to the return and reference plane of the board or not. And as we mentioned before, we need to make sure that if we use the filtering in here, we don't just bypass them with the other direct connection to the return path. So in this case, since this is an Ethernet connector, we have to comply with the standards for the gigabit Ethernet. So this connector here already integrates the magnetics, which are designed for 1000 base T applications. So if we make a direct connection to the return plane of the board, we will bypass them and make them inefficient. So this pin instead should be connected to the chassis, as we already specified for the USB, so that it becomes a continuation of the Faraday cage. As already noted before, we need to use some strategies to denote the differential signal nets so that we can guide the layouter, even if we're going to be the one doing the layout later on. Also, this is one of the points that are very important during a project review, because it will help the reviewer identify quickly the nets that are more prone to have EMI issues. Then, another important tip is regarding the characteristic impedance requirements of the transmission line. So we can write what are the characteristic impedance requirements that we will have to satisfy when we're doing the layout, so that then later on we avoid the mistakes. For example, for this type of interface, we need to maintain a 100 ohm differential impedance. So we can add this node directly in the schematics page. And also, what's important in here is that we will need to be extra careful in laying out these nets properly to avoid the intra-pair skew. So within the differential pair, for example, between TD1 plus and TD1 minus, and to avoid also the interpair skew. So between differential pairs, for example, TD1 and TD2. So what is it going to be important here is that the skew limits are defined in time, not length. So when we are measuring the links, we need to focus not so much on the length matching, but rather on the time matches. So on the propagation delay skew, which is the time of flight differences. And this then will account for the variation in the signal propagation velocity, which depends on the effective dielectric constant of the substrate, but also on the trace geometry, but also on other factors. And especially for this type of high-speed connections, we have to be careful that we design the differential pairs as symmetrical as possible, so that we don't have the conversion mode of propagation where we have the differential mode currents turn into common mode current. And why this is extremely important? Because the common mode currents are much more effective at predicting emissions. So for just a few microamps of current, we will be already out of the emission limits. So these are all important information that can be included in a side note of the schematic page or even in a table. Now let's evaluate the schematics of the HDMI block. So as already mentioned before, especially for the HDMI cable, we want to be careful on how we connect the shield to the connect. So in this case, the HDMI cables are particularly problematic and also a high source of interferences. And it's easy to find HDMI cables with cheap pigtail connection, like I was saying before, they break the Faraday cage effect meant to be provided from the shield of the cable and the shield of the connector. So this is why it's important to know the fundamentals behind the decisions and not only apply the rules of thumb, because in cases like this here, where it depends mostly on the applications, you need to know the principle behind so that you can answer the tricky questions. So awesome job on having the transient protection also here. Like we said already, this is a fundamental requirement, especially in interfaces like the HDMI, which are often plugged and unplugged, increasing the risk for transient interferences. Then the remaining improvements for this schematic page, they are the same that I already mentioned before. So differential pair notations, direction of the schematic block, impedance requirements, and so on. And of course, these tips, they you not only apply for one page, but you can apply them to all other pages as well. So of course, in future projects. Now let's move to the USB schematic. Here we have a current limit switch. Then we have transient protection for the data lines. And just as a quick tip in here, we can place the GND symbol pointing down, since these can be a little bit misleading when reviewing the schematics. And actually it looks like a power port with positive voltage. So having a down pointing orientation is also a good common practice. Here as well, we will need to add the information regarding the data lines, communication speed, and also the impedance requirements, so that it becomes easy to design, but also to debug in case of any issue. So same comments goes for the differential pair lines, as I said before. So we need to set them up correctly with the proper net classes and also to distinguish them from the regulars one. Then up next, we have the PCIe M2 schematics. So here, as we just mentioned it would be important to have the specifications noted down somewhere. So PCIe can be problematic as it runs also at high speeds. So we want to make sure that the right annotation that will remind us the right precaution when designing this board. So same comments also here for the NAT classes. And the other thing to watch out here is for the DC-DC step-down converter, which we step down from 5 volts to 3.3 volts. Because this is where we have the readaptation of the energy distribution. So because we have to convert the energy from one voltage to another, which essentially chop the energy as required. And so there in the chopping part of the process is where most of the high energy harmonic content is, which means we have to watch out how we do the placement of the components, as well as watching out to how we design the layout. Also, this one is one of those components that once the board has been assembled, can be easily analyzed with a near-field probe to check its harmonic spectrum. Then the other crucial component here is this 82 kilohertz crystal oscillator. And this is definitely one of those components to watch out for, since it is required that it has a sharp rise and fall time, which again translates into high energy harmonic content because we have this conversion of energy. So this component, we need to have short tracks in order to avoid having any of those harmonics, then turning this track into an accidental antenna, or even simply allowing the EM fields of the harmonics to countless other traces. So talking about the crosstalk in this case. And then these crosstalk can eventually turn into EMI. What we can do in here is add some notes to watch out for the layout of this component and to keep the tracks as short as possible. Then here we have no protections against the transient effects, but the M2 slots, especially in consumer or industrial devices, are often exposed to environments where the transient effects can occur. So think when we are inserting the card or removing the card, or even in high static environments. So since this is actually an open source project where the applications are endless, we can perhaps add more protection in here. Now, let's quickly take a look at the DSI-CSI interface. So the DSI display serial interface and the CSI, so the camera serial interface, are high-speed serial communication interfaces. And particularly, we find this in mobile and also IoT devices. So this is also one of these interfaces that we will have to watch out for. And in fact, it's not uncommon to have EMI issues from this type of interfaces, especially when the ribbon cable gets quite long and we have more chances of it becoming an antenna. And since this is also a connector to the external environment, I would personally add the more protection here, so some more transient protections. So we have to remember that all these points will be tested during the EMC test. So we want to be prepared to handle them properly. But most importantly, these points will be stress tested by the users, which sometimes are imposing even harder tests on the device than the labs. So we need to make them extra endurable. And as usual, all the recommendations that I made before, we also apply to this page. So differential pairs and annotations, we will need to place them also on this page. Now, moving to the input and output schematics. Here also we have some various connectors to the outside world, which will require appropriate protections. Also here, I would recommend adding some descriptive blocks that will help better identify the functionality of these blocks. And a special consideration here needs to be given to the reset line, since this is going to trigger the reset of the system. Because this is a line that often is left as not really important, but it is actually one of the most important lines that we have in a system. In fact, here we can have some signals that couple to it, and then it could reset the board during some important tasks. So we need to make sure that this does not happen. And a note for the layout will definitely help in this case. Also here we can add a tip to add the net labels to all the connections in order to avoid having random net names during the layout, which just risks creating confusions and mistakes later on. Now, the last page is the CM5 page, which only contains the two connectors that allow for the connection with the CM5 modules. And beside the tips that we have shared so far, we don't have many recommendations here at this point, because it's very simple as a schematic. All right, so let's analyze the layout of the board. So this, as we mentioned, is where we have most of the work that needs to be done. Because in the schematics, we can verify that the components and protection have been set correctly, but the PCB layout tells us how the electromagnetic fields will interact with the physical world and with our circuit. So majority of what it takes to pass EMC test and the first testing cycle is done here before the board even reaches the EMC lab. So if you're designing boards where you need to pass the EMC test or not, making an EMI review will definitely increase the quality of your board and the robustness of your system. First impression, the PCB layout looks clean and professional, which is always a plus. And right before we check anything else, we can analyze the stack up of the board, because this will give us an idea on how the energy is channeled within this specific board. If the stack up is not set up correctly, the chances are that the rest is going to be a little bit problematic. And actually, this is perhaps the most important and less forgiving point in the design for EMI control. So selecting the right stack up requires you understanding on how signals propagate in a printed circuit board, which deep down it means how the energy is propagating in the dielectric and not in the copper layer itself. Most importantly, how the copper layer acts as the boundaries for the signal and not as the transmitting medium. And unfortunately, we are taught in school that the copper is where the signal is. So the electromagnetic fields propagate without even talking about the dielectric. In reality, it's the opposite. So the dielectric is where the fields propagate, and the copper, or the so-called conductive materials, act as the boundaries to contain and channel the fields. So this is also why, in my opinion, we have so many other misconceptions and doubts on how things really work. And also why so many engineers fail EMC tests with their product, because they focus on the wrong problem and honestly learn the wrong phenomenon. That said, before checking the physical properties of the stack-up, such as material, dielectric, and thickness, we can take a look on how the layers have been arranged and also in what order. So we can go through each layer and then take a look at the manufacturing properties of the board to verify that we are not going to have any issues with DMI from what concerns the stack. So starting from the top layer, we can hide all non-complete layers so that we don't get distracted by irrelevant information for the moment. And I will only leave the top layer active for some inspection. So the top layers appears to be clean and well organized. And my goal here is actually to spot for common issues like crowded areas and signal traces that we ring the bell for things like a crosstalk or antenna-like structure, for example, with copper polygons or even impedance discontinuities. And so some areas we have to dedicate special attention to. And if you hear even some PCB manufacturers, they will recommend you to pour the copper all over your layers so that you have a balance between the layers. So this helps prevent the manufacturing issues and also thermal instability caused by the warpage. However, copper pours introduce also some considerations. So the first one is the antenna-like structures, because copper cores are still conductors, so they can act like antennas if their shapes or positions are not carefully managed. And so isolated islands or areas connected at only one point, then they create impedance mismatches. And so these mismatches, then they cause voltage variation when signals coupled to the copper, especially with return currents. And so this is what then can generate the common mode currents, which can cause EMC test failures. And so antenna-like structures like the copper pores can also create resonances or even slot mode antennas. So we need to be extremely careful with it. And one important tip here is that just because we connect the GND net to a polygon, this does not mean that this is going to be 0 volts, or doesn't mean that the current is going to sink there. Because the word ground is simply an outdated concept, and it is actually a concept that brings more problem than benefit. And that is also why I try to avoid using this term as much as possible. So the fact is that even if I connect the polygon to the GND net, this will still have a certain impedance, and its shape can be as a resonance structure for certain harmonics contained in a signal. Then the other issue is that copper polygons affect the impedance a signal sees during the propagation. For instance, in order to control the characteristic impedance of the traces, we must consider not only the geometrical properties of the traces, but also the traces position relative to the return reference plane. And not only that, but also to other conductive structures that can influence the propagation of the fields, as well, of course, as the dielectric, which is where the fields actually propagate. So this is because the polygon pore then modifies the electric field distribution around the trace. So when we place any conductive structures, we are changing the environment that the fields will experience. And this will result in a change of instantaneous impedance, hence also the characteristic impedance. So ignoring these can lead to real impedance differing from calculated values, and these can simply translate into signal integrity issues, but also into EMC issues. I usually avoid the copper pores, especially in dense layout, because in my view they add the complexity without enough benefits to justify their use. In my experience, both my boards and my clients' boards have performed better without them, and besides, when using them is not trivial, and they require you to perform at least a simulation so that you can be sure not to encounter issues due to their presence on the board and that they serve for the purpose that they're meant to serve. But I understand that others may have different preferences, which is fine for me as long as it works for them. I generally do not recommend them unless you really know what you are doing. The other improvement worth noting in this layer is regarding the accordion style routing on the differential pair nets. So I prefer to design smaller bumps like the ones at the bottom, so that we can reduce the crosstalk and minimize impedance discontinuities within the differential pair. And here it is also worth remembering, as already mentioned before, that we don't really care about the length matching, but rather the time matching, but also about the integrity of the signal through the whole propagation. Then another important point here is the lack of vias from the pad to the return reference plane. So the way that we reduce the impedance here, most importantly inductance, and avoid creating common mode currents is by placing the vias from the ground pad to the return reference plane, which is also called the RRP for short. And by placing them in proximity, for example, here in the M2 3v3 vias, so the way that we can reduce impedance here, most importantly the inductance, and avoiding creating common mode currents is by placing the vias from the GND pad to the return reference plane, which is also called RRP, and by placing them in proximity to the M2 3v3 vias. So in the way that this has been designed, we are essentially forcing the return current to find a higher impedance. And in turn, this will create some common mode sources and also increase the differential mode current loop, which generates higher emissions. So many engineers know the general EMC guidelines, but the difference between them and the specialists is to know this type of nuances. So the fixing here, like I said, is to add the vias from the pad, the best option being in-pad vias, or as close as possible to the pad anyway. But also adjacent to the M2 3v3 vias, so the one from the signal trace, and to connect these vias to the return reference plane for low impedance path. And since we are discussing the return reference vias, which are called also RRV, we have to verify that all the signal transition layers have at least one return reference via adjacent to the signal via. So in this way, we ensure that the signal during the vertical propagation, so when it's crossing layers, has also the appropriate potential reference and also the return path. So the idea is to have 360 via structures, and the minimum is to have at least one via. Of course, this depends on the type of signals that you are transmitting, but in general, one via has to be there. And a question that comes often here is this only required for high-speed signaling? The answer, of course, is no. And especially if it is something that brings a lot of benefit and it's free or cheap to do it, then we can just do this. But at the end, it is a requirement anyway, because this is simply how the signals propagate. Now, stitching vias, I see that we have some nice stitching vias all around the perimeter of the board, which is great, because it's sort of creating the Faraday cage effect that I was discussing before for the chassis. Obviously, this is up to a certain frequencies, and this is already a nice upgrade. But what I think that we can also improve is to add more stitching vias to connect not only the polygon pools on the layers, but also so that we can make the return reference plane used on this PCB, which we saw on the GitHub page is actually 2 of them, and we can make them equipotential between each other. But also so that we can increase the resonant frequency of this plane. Because yes, in this case, I want to increase the resonant frequency to a higher value so that I bring it above the frequency of interest for the EMC test, but also for signal integrity requirements. Because the planes are pieces of conducting material, so they hit certain natural resonant frequencies. And if this is too low, then I can have this resonant frequency in the range of testing, or even they can disturb the signal integrity aspect of the signals of my board. So when I place the stitching vias together between these two planes, I then decrease the cavity created by the planes and the stack up. So the resonant frequency shifts to the higher end of the frequency spectrum. The other benefit of having these stitching vias is that now my signal can find more low impedance points for the return currents, which it ends up reducing common mode, but also differential mode emissions. Okay, so now let's move to layer number 2. And so this is exactly what we want, a solid return reference plane that not only provides a reference for the signal potential, but also a low impedance path for the return currents to close the current loop. Because unlike the power plane, which typically does not fully provide both of these features, a solid GND plane is the best option here. And this plane should have no splits, cuts, larger hole, or gaps that can create impedance discontinuities. Or they can create a situation where the signals on the top layer then it crosses the gaps on the second layer, so on the return reference path. Because when this is done correctly, as in this design, it ensures that we maintain the proper signal integrity and also the proper return path. So kudos to the designer here for making this choice. And also, just as a side note in here, I said that the power planes, they do not provide a return reference as good as the GNDnet in this case. And since this requires a more in-depth explanation, which I already gave in the EMI design course, I would want you to check this first. Now let's move to layer 3. So this layer appears to be used for signal traces, which is actually similar to the top layer and includes a copper pool connected to the GND nets. I see some traces running a little bit too close to the edges of the board. And my other remark is that the certain traces here, they could be spaced farther apart. There is actually plenty of board space available. And when we increase the spacing, we then improve overall the signal integrity by reducing the crosstalk between the signals. Of course, course, also the previous remarks that I made for the top layer, they will apply in here. Now, moving on to layer 4, this layer is also not crowded. So the copper plane here is connected to the 5-volt rail. So it is primarily used for power. Then we have traces on this layer that also carry other power rails. So this setup is good so far. However, since this is a power layer, what I would expect on layer 5 is another ground plane. So we saw that this was the case when we were checking the GitHub page. And so if we have in the layer 5 the return reference plane, then this one can provide the return reference plane not only for layer 4, but also for the layer 6, which, as we saw before, was also routed with the signal traces. Because if instead I place another signal layers here on layer 5, not only I do not provide a complete propagation for layer 5, but also the energy delivery from layer 4 gets corrupt. Because in order to deliver energy, which, as we should know already at this point, does not come from the copper layer, but it comes from the dielectric. So we need to channel this energy between the power plane and the return reference plane. So in this particular case, the 5 volts and the GND plane. So we need to remember that the layers always go in pairs. So signal layer with the return reference layer, and power layer with return reference layer. And the return reference layer has to be adjacent, but also as close as possible to the signal or the power layer. And so the other point worth mentioning here is that if the power layer is not necessary, we can simply route the power as traces. So what does it mean when it's not necessary? So when I do not have a high current requirement, for instance, and when I don't have very low target impedance requirements. So these are two examples. So we need to remember that larger planes have lower resonant frequency, and this can end up being in the spectrum of interest of my signals or of the EMC test. So when not needed, it is okay to use tracks and then use the remaining space for other signals routing. In the case of this particular boarding here, where we have such a high-speed signals, we need to make sure what is the target impedance of the power delivery network that we are after, and then we can choose the best PDN strategy accordingly. Now, moving to layer 5, we can see that we have the return reference plane, as in the case of the layer 2. And so this complements the stack by providing a solid reference for the adjacent layer, including the layer 4, which is power, and the layer 6, which is signals. So in this way, the first 3 layers of the stack are symmetrical to the last 3, which is the correct way to design it. So what will be important later on will be to verify that the layer 4 and 6 are close enough to the layer 5, which is the return reference plane. So the signals on layer 4, they don't end up coupling to the layer 3. And the same, of course, we have to verify for layer 1 and 3, making sure that they are close enough to layer 2 so that we don't have crosstalk interference between the layers. Now, last and final copper layer is used for signal routing. And here we can probably say that there is not much new at first glance so that we haven't discussed so far. So we will need to apply the other tips that we shared before also to these layers, keeping the distance, also checking the impedance of the traces, return reference vias, and so forth. Okay, so let's give a quick stack-up recap and let's take a look at the material choices. So as we have seen, the layer stack-up is as follows. Signals on layer 1, then on layer 2 we have return reference plane, then we have on layer 3 signals, then we have on layer 4 power, then we have on layer 5 return reference plane, and on layer 6 we have signals. So as already mentioned, notice the symmetry of the first 3 layers and how they almost mirror the last 3. So this symmetry will be useful, especially with manufacturing and thermal behavior, and also in producing a board warping. So now what we can also see is the physical stack-up, which is the most important point, and it's actually where the signals or the electromagnetic fields exist in the board. So we said this before, the electromagnetic fields propagate in the dielectric space. So now we can see where the dielectric is. And so we also said that the copper layers, they are only the boundaries for these fields. So the copper layers are there to contain and to channel the fields in the dielectric space. And so this is also why layers must be paired. So 2 boundaries are required to confine the fields, because a single layer cannot contain the fields, which can lead then to EMI problems. So the copper layers are not there to propagate the signals, but only to channel and contain them. And this is actually one of the most important points I can share here. So this means that if the stack-up is properly designed, we should have the layers with two copper layers in pairs and the dielectric between these two layers. Specifically in this stack up, the pair here should be layer 1 and layer 2 with dielectric 1 in between them. Then we have the pair formed by layer 2 and layer 3 with the dielectric 2 in between them. And now, taking the symmetrical portion of the stack up, we have the pair formed by layer 4 and layer 5 with the dielectric 4 in between them. And the final pair would be then the layer 5 and layer 6 with the dielectric 5 in between them. So notice that the space where the signals propagate will be dielectric 2, and then we will have dielectric 4 and dielectric 5. So the next verification step that we have to perform here is to ensure that the spacing between layer 2 and layer 3, and then layer 4 and layer 5 is less than the spacing between layer 3 to layer 5, because this prevents signals from spreading into the dielectric between layer 3 and layer 4. So we're talking about the dielectric 3, which reduces the crosstalk between these layers. Because if layer 3 is too close to layer 4, it could use layer 4, which is the power layer, as a return path, which is problematic because the power layer is not continuous and will introduce then impedance discontinuities. And this is one of the verifications that we can verify now, but then we will confirm also during the simulation with the SimBear. So let's verify the stack up by checking the thickness of the dielectrics between the layers. So dielectric 1 is 0.1 millimeters, dielectric 2 is 0.5, then we have dielectric 3, which is 0.13 millimeters, and then we have dielectric 4 and 5, which should be mirror image of dielectric 1 and dielectric 2. So we have 0.5 for dielectric 4, and then dielectric 5, which is 0.1 millimeters. So in this setup, we should have actually stronger coupling between layer 3 and layer 4 than between layer 2 and layer 3, which is really not ideal, because the stronger coupling across the layers that are not intended as a signal return pairs then will cause these impedance discontinuities and increase the crosstalk between layer 3 and layer 4. So the goal is to have a stronger coupling within the paired layers and, of course, the dielectric in between them. So this choice can actually result in issues later on. And we will verify this with the SimBear, which will give more details on that. Now that we have reviewed the stack up, let's look at the details regarding the characteristic impedance of the traces. So we know from the schematics that we have several high-speed connections such as the USB-C, Ethernet, HDMI, PCI Express, and DSI-CSI connections. So one key requirement for these signals is that the transmission lines have a well-defined characteristic impedance. So this is essentially the impedance which characterizes the transmission line. And the definition of impedance at the fundamental level is simply the ratio between the electric and the magnetic field. So our job will be to keep this ratio constant for the whole propagation of the signal in the dielectric space between signal and return and reference conductor. So essentially in the dielectric. And if at any point during the signal propagation, the structures changes and has an impact on this ratio, then also the signal changes. So this simply means that we need to engineer the channel where the signal propagates to be as continuous as possible so that we can preserve the impedance. And now, as I briefly mentioned before, these high-speed protocols can have different characteristic impedance requirements. So this is also why it's important that we note them on the schematic page, so that we then start doing the layout and we know what the target is and also how we can engineer these channels effect. And every time we are unsure about the required impedance for these protocols, you can look it up even using some AI tools. And if in the worst case scenarios, you have no access to any AI tools or even web, then design the traces to be 50 ohm single-ended impedance, so which is probably one of the most common ones. So worst cases, you are not wrong most of the time. So what are these parameters that affect impedance in a PCB and which of them can we control? So the characteristic impedance depends on the physical geometry of the layout. So track width and thickness, then distance to the return reference plane, dielectric properties and thickness, and also the adjacent conductive structures, as we were saying before for the polygon pores. So in essence, the physical properties and structures of the transmission line channels. And it's important to design with electromagnetic fields in mind, not electron flowing through the copper. And why is that? Because the signals do not propagate inside the conductors. So they propagate as electromagnetic fields surrounding the conductor and in the space between the conductors. conductors. So other nearby structures can interact with these fields, then affecting the signals. And so this is why we carefully control the distance between the signals and the reference conductors, the dielectric material and its properties, the placement of additional conductors that can influence how these fields are contained in channel. And without the proper return reference conductors, their fields are simply unbounded, so leading to higher emission and signal integrity problems. So when you understand the signals as electromagnetic fields rather than just the current flow, then everything starts to make real sense, because then you can think about the correct layer placement, the importance of dielectric thickness and conductor spacing, and also why the control impedance matters, because mastering these fundamentals make the design much more intuitive. And then you no longer need to rely solely on simulations or computational tools to guess what will, because understanding the physics first allows you to make the right design decisions from the beginning. Okay, so now that we gave an eagle-eye review of the layout, and before we run the simulation with Symbior, we can do a review of the 3D model of the board. And so this will allow us to understand from the components and cable perspective how the board might perform in terms of EMI. So to start with, the design looks nice and professional. And I'm not too sure if it is because of the library or some other reason, but it seems that I cannot visualize the 3D models of certain components. So anyway, what is important to see at this point is how the connectors are placed. So ideally, you want to have all the connectors placed on one side of the board. And you want to do that because once you plug in all the cables on the board, if you have them on one side, then the risk of creating antenna structures is much lower than when you have them on multiple sides of the board. Because if you think about it, when all the cables are connected, you essentially have an EMI source on the board, because this is when you have the conversion of energy from one state to the other, like, for example, DC-DC converters, ICs, and so on. And then you have these long cables that act as your antenna structure because they are connected to the board, which resemble an actual antenna dipoles and other similar antenna structures. So the chances that you radiate emission is much higher than having them on one side. And this, of course, depends also on the proximity of the return conductors to the signal conductors and to the arrangement of the cable in respect of other conductive structure, for instance, the earth ground flow. So this is one of the points that we will have to watch out for and to actually verify with a pre-compliance test, even if it's an in-house with the current probes and spectrum analyzer. Okay, the next point here that is catching my attention is the tantalum capacitor. And I will simply get rid of it and place here a ceramic capacitor instead, because they are not really reliable and also have some safety concerns. So I also want to point out something that might not immediately be obvious. So since the CM5 module will be placed above the board using this connector, it will create a cavity, so a space between the module and the carrier board. And both the boards have high-speed signal, so we need to ensure that this cavity does not become a resonant cavity. In other words, we need to verify that it is not acting like an antenna if any harmonics of our signals happen to resonate with this cavity. So one of the things that we can do here is, for instance, use these new EMI materials that will be placed in between the cavity, essentially reducing the cavity that we can. My other tipping here would be about the connector shields. In particular case where we know we have a metallic shield, we can make sure that the shield is connected to the chassis with a low impedance 360-degree connection. So this will act as a continuation of the Faraday cage, as I was already mentioning before. And if we have the shielded cables, then this cage will simply be continued farther thanks to the shield. So many of the EMI issues are due to connector shield not properly connected, or because the cable connected to it and their shields are also not well connected, and then they form this pigtail connection. So in the case where there is not enough a contact point between the connector shield and the chassis, there are some EMC gaskets that we can use. So as for the rest, I can already see many good practices. For instance, the use of annotation to indicate pin 1 of the ICs or the direction of the polarization of the components. So these are all plus points. So now it's time for us to run a quick simulation of the board using Symbior software, which is a complex electromagnetic and signal integrity software. And one of the things that we have to do is to check that the channels are designed with the correct impedance profile. So in the design files, we can see that we have a note on the fabrication layer regarding the width of the tracks and also regarding the spacing. So these are most likely the requirements for the differential impedance of the differential pairs used, and they're probably already given for the stack up, which is selected here. So this means that the distance from the return reference plane is already accounted for in these calculations. Right? What I do not think is accounted for is the presence of the polygon pool next to the signal traces, which also has a large influence on the characteristic impedance of the transmission line. So this is something that most design give for granted, but anything that is placed adjacent to the transmission line alters the electromagnetic fields. So Symbio performs complex simulations to verify if your design meets the signal integrity, and since the electromagnetic compatibility requirements are closely related to it, we can then also use the software to prevent EMI issues and fix them right away. Because as I like to say, EMC problems are simply signal integrity problems in disguise. So the simulation process is actually fast and straightforward. And this is one of the main reasons why I really like this tool, because I think that one of the highest barriers to entry for the simulation software, I mean, in general, is actual speed of execution. So how fast can I learn the tool and use it for my objective? And in this example, to perform the simulation, we need as a first thing, export the project as the ODB++ files, which we can easily do on KiCad in the fabrication setup. Then we can load these files on the Symbio software and create a new solution so that we can extract all the project information that is going to be relevant to make this simulation. And of course, before running simulation, it's important that we verify the load stack up and that the information of the project is correct. So one of the things that we need to verify, for instance, that the electric thickness matches the designer specification and the manufacturers, and that they are actually accurate. Then we can check that the information regarding the physical stack-up is provided after the manufacturing process, like laminations and pressing, where the material can shrink slightly. And in essence, we need to make sure that the input for the simulation is as close as possible to the finished product, so that we can get the results that are going to be as close as possible also to the real results. And this is important because an inaccurate stack-up can already throw off the simulation by 10 to 20% or more. So for the sake of this particular simulation, these are all details that are a bit out of the scope, because Symbio is such a great tool that allows us to define most of the parameters. So we have access to a lot of details, and then many can already feel overwhelmed by this. And so this is also why here I just want to share the method. But if you're running high-stakes simulations, you need to get familiar with the tool and check that all the information necessary for the simulation is correct. Otherwise, you will get data that will have a higher margin of error, and so you will have inaccurate results. And of course, if you want to go more in depth in this type of training, you can check my courses and also join our academy, where we're constantly adding new content and material on this topic. Also, not sure if I mentioned this already, but you can get the software at symberian.com, and the verified license is fairly inexpensive, and it can massively speed up your workflow and project schedule. And depending on the time you're watching this video, we might even have some coupons for you guys to try the software and get familiar with it. So check out our academy for that. All right, now let's start the simulation for this design and see how this project will perform. So the first thing I do is to create a new solution. I give this a name, and then I will proceed to import the ODB++ files, which essentially imports the project files to perform the simulation. So here I choose the file which I exported previously from the CAD tool. In my case, it was KiCad, but other CAD tools will do the tool, as long as they can export it to ODB++ files. And then you can see that once I uploaded the files, I can already see the shape of the board. Now, all the project information is ready for the simulation. So we just need to verify the stack up and then indicate what are the signals that are going to run on each net. So how can you find the current information of the stack up? You can just check this under the project tree. And then if you already have the adjusted stack up with the real parameters, you can simply upload it on the software. So you don't need to input the parameters of the board, but you can also upload the modified stackup if you want. Symbio allows you to do that too. But this is a simple project, so we're only going to use the simple features, but Symbio really gives you full control of many parameters and details that allows you to run even very complex projects. But now I don't want to make this into a step-by-step Symbio tutorial, so I will go quickly to the process. And then if you want to deep dive, you can check our trainings. So once you make sure that you have the physical properties and materials, you then need to select the analysis condition. So we can select what is the signal that we're going to test our board with, and also the types of tests that we are going to perform on the board. So here we can select the channels either on the board view or on the right-hand sidebar. And for this particular case, I can simply select a random net. Let's say I want to see how the PCIe PI RX differential pair is designed. So I have to tell Simber what are the parameters of my signals. And in case you're simulating someone else's design and you're not familiar with the details requested to perform the simulation, you can then turn to AI and see what comes up. So for example, here I will take a screenshot of the data that I need. And in this case, I will use Grok and I will give the AI some context. So I can write something like, I'm running a simulation on Simber for my printed circuit board, which is a carrier board for the Raspberry Pi Model 5. And I need to test the links on the PCIe interface in the RX differential pairs. Can you tell me what are the parameters input that I need to write in the picture from the screenshot in here? And then I just paste the screenshot. So then to make sure that the information is correct, you can also ask another AI and compare the results. So one thing that I want you to notice here is that you can even upload the specific protocols to which you want to simulate your board against. So you don't need to do this input and search for the values every time. You can also save these parameters once you have already used them. So now that we have set the conditions, we can also set up which simulation we want to perform. And we can find this under the tab of the compliance conditions and measurements. So I want to start with creating a report for the reference integrity violation, which essentially makes sure that at any point in the channel, I have the reference for the signal layers. Then what I also want to evaluate is the impedance continuities. And this will check that we have achieved a characteristic impedance, meaning an impedance which characterizes the transmission line. So this will check that each point of the transmission line have the same instantaneous impedance. And then what I also want to evaluate is the crosstalk noise. So how much cross-coupling interference am I going to have with other nearby transmission lines? Then when I'm ready, I can just click on the run and Simber in seconds will generate the report with all details and instructions. So here you can also switch to the 3D view so that you can see how the impedance profile will look like. And you can see that essentially this point is where I have most of the problems. But again, this does not factor in the connector and its impedance profile, because since I didn't input this in the software simply does not know this. So you can also see that it performed the simulation against the transmission line channel next to it. So verifying the local coupling, so the crosstalk with the other channel. And this is telling us that for the signals that we are running in this transmission line, we won't have any issues. And to show you also how this will tell you more on how to fix the issues, we can uncheck the skip loss severity violation, and then we can run the simulations again. And you can see that it tells you exactly what you need to do to solve the issues you have. And now, of course, this was only one link, but we can also test other links, so other channels against some generic signals. And so we can see where our design will start to fail. For example, here I select all the signals and I keep the previous signal test to perform the simulation. So this will be checking that all the selected links will run with the PCIe testing signals at 8 gigabit per second, which is essentially the signal I used before. And of course, this is above our requirement, so we can even choose a less stringent requirement, because not all the signals on this board are going to be running PCIe signals, but we can still test the performance just to give us a glimpse. So you will also see that the report will show us more issues, and then the best thing is that many of these fixes will be free to apply. So you can just correct this point fast, and then you can continue the project. Also, the other caveat is that the power traces are selected, so the issues are much more than in reality. But if you take care of selecting the right nets with the right parameters, you can get very accurate results. Now, one of the points we were supposed to check was that layer 3 was using layer 2 as a reference plane instead of layer 4. And so when running the simulation, you can see that my remarks were actually correct. So here, layer 3 is referencing layer 4. And so as I mentioned with the stack-up analysis, for instance, this one here where there is no reference and signal is actually crossing the split formed by the layer 4. And so this is also why you don't use power layers as reference plane, because you're going to experience much more issues. And this is typically because the power plane are split into multiple planes. And so the likelihood that you cross a split above a power plane is much higher. And as I was saying before, I already explained this in much more details in the course. And this mostly depends on the displacement current and how how this can create some common issues. Anyway, what I want you to get out from this demonstration is that with a quick simulation, you can find the issues on your design and also how to solve them in the design phase. So without having to wait at the EMC chamber to find out, or even without the need to produce the board and then discover that you made a mess. Of course, when you gain expertise and become an EMI specialist, you will start to recognize the pattern. So the simulation will mostly provide you the confirmation of the issue that you already noticed, but of course, it will also take you a lot of time off and improve the efficiency with which you can review the project. So also increase the output of your work whilst reducing the input. And in this way, you can actually leverage your expertise, but also the tools to increase your profits and maximize the value that you can deliver to your clients or your company. So if you enjoy this type of content, let me know in the comments below, and make sure to check out our website and community to find out how we can help you master EMI control and become an EMI specialist yourself.